just go over it again, maybe in a different way, short version. But as we know, at least if you've read the book, at least that section, electric flux, it's just a measure of electric field through a given surface. Electric field itself, it can't flow. It doesn't flow. It's just there, but it's just it's a way of describing the electric field at any distance, from a charge, from the charge or a charge distribution causing that field. So this electric flux through a closed surface is defined the following way. The integral is over the entire closed surface, and the result is a scalar quantity, of course, a dot product. Two vectors is a scalar. Consequently, our flux, total flux, net flux, is a scalar. So E dot dA is the component of the electric field which is normal to the surface. I think that's probably the best way to think of this. And the net electric flux is the sum of all the normal components of the electric field all over, the closed surface.
Professor?
Yeah.
Do you mind going back to the previous slide quickly? I wasn't able to get the equation for hollow sphere electric field.
Well, okay, this will be available to you. You do have access to these slides, right?
Yeah, on Canvas. Thank you.
Okay, but yeah. It's kind of interesting too, how sigma is defined is the total charge divided by the surface area. And for a sphere, that's 4 pi r squared. So you can see this is equivalent to the total charge on the sphere. Concentrated. The way it's expressed is like it's concentrated at the center as a point charge.
So why is the field inside the sphere 0 everywhere, but in the previous example it wasn't? Like the cylinder?
It was. Inside, it is everywhere is 0. Yeah. This is outside, I believe. And inside, it's 0 everywhere.
I think he means the part with the red and the gray.
What's that?
The part, the problem that had the red and the gray shades.
Oh, that one's not hollow, so it wouldn't be 0, I don't think.
Oh, well, the one that's hollow, are you referring to one that's solid?
Yeah, the solid one.
Ah, okay. I'm sorry. Well, that's, yeah. In this case, it's not 0. I mean, it is 0 in the X and the Z direction. It's from symmetry. But remember what I said, if we were to go back to this part here, this is making a statement that regardless how thick the shell is, regardless how thick it is, the electric field is still 0 inside. Okay, is that understood?
Yeah.
Okay, this is just really bootstrapping this result to here. I mean, let's say this gray part, we somehow can scoop out all the charge, this inside, and we're just, the only charge that's left is in the red part. Okay, well then that section of the red part does not contribute to the electric field. It's 0. It gives a 0 contribution. It's only the part on the inside here that contributes to electric field.
So for something like this, as soon as you were to poke a hole in the center of it, then it's considered a cylinder and then it's 0?
Poke a hole in the center.
Yeah, if you poke a hole in the center, then it's considered a cylinder.
Yeah, it's a cylinder. I mean, it could be a cylinder shell, like a pipe, for example, or it can be a solid cylinder. I don't know, like a post or something. Some of these are solid all the way through. And either one, I would call it a cylinder. I don't know. Am I incorrect by that?
So just to clarify, the gray shaded area on the inside, is the electric field 0 there or not 0 there in this example here?
where the point that I'm in now, if I don't know if we're going to get to this problem, but actually I think there's one of the examples in this chapter, but it's only the part that's on the inside that contributes to the electric field. Now, if I were to, and the issue here is that this point has to be right at the boundary. If I were to bring this point downward, then I would have to bring the gray, the red shading along with it. Because I keep coming back to here, this part.
Does all of the contributions cancel though, each other
Yes,
out?
it does.
Okay, so, but regardless of whether it's solid or not solid, that electric field is still zero, even though the inside is contributing, those contributions cancel each other out.
Okay. I don't know if I'm understanding the statement but in this case, I think it's clear that the electric field should be zero inside the white part, inside the hollow cylinder. Is that agreed upon?
Yes.
All right. And if we were to take this cylinder here, it's a solid cylinder, and let's just remove out this center part here, the gray part, and our location is right at the boundary of the empty part, and the red part is still there. We still have charge on the red part of that cylinder. In that case, the electric field will be zero everywhere, right?
Right. Okay.
So it just does not contribute to the electric field. But now let's put back this center part. Then it's almost like being outside of this portion of the cylinder. We're outside of this inner portion. So it still contributes. It contributes in a Y direction, at least according to based on this coordinate system.
So would the electric field there still be like the 2K lambda over Y?
No, because you would have to remove this portion of the charge. It does not contribute. And it should go, being that it's an area sort of thing, you would have to calculate the area that's been removed, or volume for that matter. I guess it's another way of saying it, because you basically have to consider the length of the cylinder if you are using lambda in this case. This is good questions, but let me try to get through the last example. I don't know if it's going to happen, but I don't know if that's understood. But you do understand though, at this point P, we're like being on the outside of this cylinder. And so the way we would calculate it is just based on the amount of charge that's inside here. It's in the gray part. And that's just more of a geometry, or I guess trig or geometry. It's really just geometry, how to calculate this.
So we can treat the calculation as if the red part didn't exist?
Exactly.
Okay.
That's exactly it. It contributes, that charge contributes a zero field, to the total electric field. It just doesn't contribute because of the cancellation and symmetry. Well, because of the symmetry, it cancels, I should say. All right, let's go on. I don't think there was any questions on this. Let me see if we can do, okay, I'm gonna try a poll on this next part. Let's just see how this works. So give me a little time here. Poll question. Great. Did not work. A question. Not sure why it's not working. This worked fine last night. Now it's wanting me to go to an email and wants my credit card. What's my credit card number? Great. All right. I don't understand. Maybe it's my connection here is different than the home that's. All right. Why is this doing this? This doesn't work, then I'm just going to have to ask you verbally. Oh, good grief. This is not going to work. It keeps wanting me to go back to, oh, wait, I'm sorry. Multiple choice. What do I have here? It's ABC. Now it's vanished. Good Lord. You already see the answers. So it's going to be easy quiz. Just don't understand why it's a question. Multiple choice. A, B, C. You guys see anything?
I just see the slide with the question
Yeah.
about flux.
Yeah. Oh, I see. A, B, C. Now I see the problem. All right. Incomplete. It keeps telling me it's incomplete. I don't know what's going on. See if this works. Well, I don't know. Are you seeing anything now?
No, there's no
Don't
poll.
know.
You do?
No.
I just see the slide still.
Oh, good Lord. I see it on my screen. All right, let's just answer this verbally. It's just launching. Oh, okay.
Yep, but there's 2 questions on it.
Oh, okay, well, just answer the first one.
It only gives A through C.
Yeah.
Okay.
And it won't let us submit without answering both questions either.
Yeah, I have the same problem.
All right, let's try again. Not to give up, being at.
Still A, B, and C.
And 2 questions.
Yeah, that's basically my mistake. I'm trying to end the polling. Well, okay, I can tell you this, D is incorrect. So that's good. This, it's either A, B, or C. So let's go with that.
Should we just put our answer twice?
I just answered both the same.
That's whatever, yeah. This is, if anything, this is a test, I guess. It worked fine last night, famous last words. Like, what could possibly go wrong? So there's a few more that have not answered. Need about 5 more, I believe, according to the polls. Just anything for right now. So I'm gonna have to work on this over the weekend. Probably should work on it in Sharp Lab as opposed to at home. So we need two more people. Well, all right, I'm gonna have to end this. Okay, in polling, share results. Well, at least, yeah, most of you got it right. It's actually A. We'll go over that in the next slide. So the definition of flux, we already know that. But in the case for the cylinder, well, the electric field, is for a line charge, goes as 1 over R, and it's in the radial direction. So if we use a cylinder curved surface for our Gaussian surface, then the field lines are such that they're perpendicular to the surface everywhere. In other words, E is parallel to dA. This is the area element on that surface. So that's nice. But if we consider the end caps of this surface, now this is a closed surface, and the end caps, they're this flat on the end of the cylinder. Imagine they kind of cut into the line charge. But the electric field is perpendicular to dA on the end caps. Or they're parallel to the surface, but the dA vector is perpendicular. So the top end cap and the bottom end cap, it does not contribute to the flux. The only thing that the only part that contributes is the curved surface on the cylinder. And if we look at case 1, so this is the relationship between electric field and a distance s away from the line charge. And we know the surface area for case 1. L is the length of this cylinder. And it's at s distance away, so that's the circumference, 2 pi s times L gives us the area. And by just simply multiplying these together, we get a flux that's 4 pi k lambda L. And for case 2, all right, we're a further distance away. So our area is 2 pi, 2 times the distance away from the line charge. But our distance, thickness, if you want to call it, or the vertical distance, is L over 2. And so combining all this together, we're just left with 2 pi SL. It's actually the same in the case 1. And if you were to go and now calculate the electric field from that, from the line charge, we're now at a distance 2s away. And so you can see the electric field is less. Consequently, our flux is less by a factor 2. So you can see that the flux for case 1 is twice that for case 2. Yeah, someone had a question, Colin? Hello? Anyone? Someone raised their hand?
No, I think we're all good.
You're okay?
So when you're calculating flux, the radius wouldn't matter whatsoever since it cancels itself out.
Well, yeah, I mean, the radius doubles, but look, the height or the length, I guess you want to call it, the vertical length of the Gaussian surface is half. So it exactly compensates that for the circumference. The bigger circumference, it's a factor 2, but the length is a factor 2 less. But what is less is, the area is the same, but the electric field is smaller because we're twice the distance away. So the flux is, in this case, smaller. Now,
Wouldn't it just be easier to say that case 1 has twice as much charge inside it compared to case 2?
That's exactly the point of view from Gauss's law. We're actually enclosing more charge in case 1 than we are in case 2. As you can see here, if you were to follow through on the flux, 4 pi k, well, that's the same thing as 1 over epsilon naught. And lambda, this is the linear density times the length, that's charge. So that becomes charge Q divided by epsilon naught. And so there you have it. This is another way of bringing forth Gauss's law. I mean, Gauss's law and Coulomb are just, they're the same way of expressing, a concept, the electric field. Usually, for Coulomb, the situation is when you apply that, it's when you have, what the charge distribution is, but not the electric field. So you use the charge distribution to calculate the electric field. It's the opposite with Gauss's typically. Gauss, the electric field, but not the charge distribution. So you use the electric field to calculate that, the flux. Running out of time. I guess we'll continue this, but this was the next clicker I was going to try. I'm going to practice this. That will be my homework over the weekend to get this down, right? So hopefully it's be problem free on Monday.